Hello? Okay. Well, hello, everybody. Good afternoon. I'm going to get started because 5 after, and we have a lot of talks to hear. We are in the External Synergies and Multi-Messenger Astronomy session. I'm your session chair, Christina Andrade from the University of Minnesota. For those who just arrived and did not see the morning events, we have a code of conduct. Please treat your fellow scientists and be cognizant of them. If there's anything you witness to communicate about, you can contact Sandrine, Andrew, or Fed about any issues. Perfect. We have a mix of Zoom and in-person communicators today. If you are asking questions at the 3-minute session afterwards, please make sure to state your name and raise your hand and wait for the microphone to come to you. If you're on Zoom, please use the chat to request to unmute yourself. You can also type a question in the chat or in the Slack channel. We have a very dense session today, so we have 7 talks. They are 7 minutes each with 3 minutes for questions. I will signal you at the 1-minute mark. If you want the 2-minute mark, please let me know. Please send me your talks, or you can add them yourself to the session page. All right, Sam, you ready?
Yes, I'll just pretty much wing this. All right, how's that look? All right, that looks great for me. Hi, everyone. This is the after lunch session, so I assume you all are well fed and sleepy. My name is Samuel Wyatt. I am a support scientist for NASA at Goddard. I'm going to be talking about across and how we hope to enable time domain and multi-messenger astrophysics. We have a good team, Jamie Kenna, who's the PI of SWIFT, so we are doing a lot with fun space telescope stuff. But the background out of the Astro 2020 decadal, TDAM science is labeled as very important. And so there was a FISCOS at NASA. They did a study and they came out with saying that they need some sort of initiative to support TDAM science through workshops. They conducted a 3-year study, and out of it came this ACROSS project. It stands for the Astrophysics Cross Observatory Science Support. And out of that, we decided that we need some way to provide software and data to facilitate TDAM science workflows, a help desk so that anyone who wants to utilize NASA observatories to do their science as efficiently as possible. And out of this, hopefully some money for grant programs as well to follow up with these initiatives. So the highlight of this talk is at the lowest order, in order to promote coordination in time domain astronomy, observational transparency is key. If I know what SWIFT and HST are doing in response to this TDAM event, how can I complement that, look at where they're looking, provide similar data sets and some sort of coordination. And so the main issues that we have found at NASA is that each mission has pretty much siloed all of their data. You want to look for James Webb, HST, SWIFT, you have to go to in many resources. This is IXP, James Webb, SWIFT, this is HST, and they all have very different formats. They all have either similar or completely missing data. And if you want to be able to provide this level of coordination and transparency, it is a lot of work. And hopefully we want to incorporate some sort of LSST as well. So each mission has siloed a lot of this data. So our initially proposed solution is what we're calling science situational awareness. It's a single interface that provides homogenized data for all NASA observatories, where they're looking when in planned follow-up, scheduled observing for all of the space telescopes. Along with that, that's the first order, what we're working on right now. But in the future, we're going to be working on how do you request observations. So kind of having what we're calling a TOO toolkit. I'll talk about that later. And also, what can you do with this data that we're providing? So we're going to provide observing tools as well. Visibility window calculators. Say you have an event and you want to see at what time you can observe it with all of these space telescopes and potentially ground-based instruments as well. Providing a single interface that can give you an answer for all that in one source is what we're also planning on providing. So what does this look like? We're using Open API to provide a web server that has all of this data on hand for observers around the world. And it'll all be in the same format. So when you query it, the data for HST, James Webb, will all look exactly the same. So you can run some tool over it and it will all be scalable in that end. What does this look like from a science perspective? We have a science event that happens. A lot of what people have been coming up to us and saying, will you be replacing us? Will you be doing this? And to what we'll say is no. Across plans to sit in the middle between the observatories and the observers. So when an event happens, there will be an alert broker. And what does this look like? We will have support that sits between both of you. So the observatories can see what NASA's doing internally, and also the observers can do that. And there'll be tools built on all of this data that will support it. So like I mentioned earlier, we're gonna have this observatory, like the suite of interesting tools that's not only gonna be a back-end API, but also have front-end interfaces as well. So live dashboards of all of the observatories, API access to for all of that as well. This, what we're calling a TDAM toolkit. This will be sitting on top of it. You can install it yourself. It'll be pretty much a Python library that will have all of the tools that you will need to perform any sort of follow-up and analyze any of the data that we provide. So it can be deployed locally, all that. And like what we're saying is we're providing across subject matter experts and our web services as well. I've been given the 2-minute warning. So you can be accessed through our data portal. You can have the API access and all of that good stuff. So bringing this all full circle, how will this facilitate what Ruben does? So this will be synergistic in a way that the way we're defining our observatories is that it's going to be a generic design that LSST will be represented as just another observatory in our system. Instead of existing in space, it will exist on the Earth, and it will be able to tie into all of our tools. Again, like I mentioned, we're planning on not only supporting just space observatories, but also ingesting Ruben's schedule. There's a plan to implement the OBS LockTap IVOA format, and we'll have immediate potential passive science analysis, find where things are overlapping. Like I mentioned, visibility calculators, follow-up requests with TOOs for NASA facilities, or any facility that wishes to utilize our service. And hopefully in the future, we'll be providing alert support. So the current future work, like I mentioned, right now, we're going to be publicly deploying in October, and out of the box, we will support all planned observations for all NASA science observatories. And then on top of that, the tools that I mentioned, coincident coverage and visibility calculators. In the future, we are having a TDAM workshop in October as well. That's where we'll be deploying this. And like I mentioned, a bunch of tools that will be built on top of this analysis. Yeah, any questions?
Hello?
Yeah, thanks. This is really good. There's another mode which you almost alluded to, which is co-observing.
Co-observing, yes.
So to facilitate that, we're going to be observing deep drilling field, at least one early on to fairly great depths. And it would be cool to co-observe in that field if possible. I mean, the fields of view of some of these facilities is small,
Very small.
but you know, we're going to in real time discover stuff. And you wouldn't have to move that space telescope very far to be right on it.
Yeah, that's a great point. There's not much of a question out of that, but yeah, I totally agree. Like being able to schedule coincident observing will be a direct response of how this data will work.
Thank you for the talk, Chris Walter. So I didn't quite get, when you do the query, is what you're getting back metadata of what observations were made, or is it links to the actual data products at the various places?
Yeah, we're going to be completely separate from the archives. So this is just out of the box. The first thing we're going to be deploying is just the metadata, like who looked where when. Like I think so much science can be enabled with that. And from there, we can also tie into already existing tools like the treasure map as well, and we can pull from there. And when we do start ingesting alerts, you can have like envision like a web page of like, this is where the supernova went off. Find everything plus or minus 1 day that observed around here. Like that will be just that metadata will allow that kind of analysis.
Great, thank you.
Alrighty, we are up for time. Thank you, Sam. Round of
Thank you.
applause. And Greg. All right, thank you, Sam. Our next speaker is going to be Gregory Peak.
So hi, my name is Gregory Peck from Institute for Astronomy in Hawaii. So I'm gonna introduce the 7-dimensional telescope, or new facilities and tools for the classification. We are living in the golden age of transient astronomy. Thanks to the gravitational wave detectors, they opened a new era of multi-messenger astronomy, and also the advent of Lubin LSST is also one of the major contributors of this era. So the demand for the rapid classification and anomaly detection for transients are getting increased. So there have been two major classification methodologies. One is spectroscopy, the other one is light curve classifier. The first one is one of the most reliable method, but is a relatively expensive observation. Also, it has very complicated process, data reduction process. And also, the second one is light curve classifier. This is a very cost effective, but it takes some time to classify some transients because it requires the multi-epoch data. And also some transients like kilonova, there are many imposters because some transients share their fast evolution light curve trend. So our facility, 7-dimensional telescope, is in the middle of two methodologies, spectroscopy and photometry. So it consists of 20 small telescopes in Chile. And I want to address this. We have 40 medium bands and wide field of view. So as a result, we can get a low resolution photometric SAD for all detected sources. So our ultimate goal is to identify the optical counterpart, the kilonova of gravitational wave source. Also, we are interested in many other various types of transients like Olic supernova and TDE or etc. If there is no transient alert like Lubin transient alert, if there's no, we are doing an all sky survey, including high cadence monitoring survey in small patches. Actually, I prepared the quiz, but I have no time, so I will show you just answer. Let's guess what transient it is, but it is really hard to know what it is through the multi-broad bands. But if we look at the medium bands from 70T, we can see very distinctive features here, silicon 2 observation line. So we can see, oh, it should be Taiwanese supernova. So this is the idea. So based on this idea, there's two goals for this talk. The first one is I'm going to show the two models. The first one is multi-class classifier, and the other one is anomaly detector, especially for the kilonova. So to train the machine learning models, I compiled the observational spectra from Open Supernova Catalog and WISE Lab. And then I generated many synthetic photometries from the spectra using this 70T simulator that I developed. After that, I extract the lots of colors to use them as input features for model training. So this is the first result. I trained the model and it shows very decent number. The performance is about 80%. It's not that bad. And also I want to say this classifier gives us the probability for each classes that I trained. So this information is really helpful to find the anomaly. So keep in mind for the next slide. These are our second result, the anomaly classifier. I use the unsupervised model, the isolation forest, and it is only trained by a non-kilonova. So as you can see, this classifier can divide two distribution, the simulated kilonova and non-kilonova, but still there's so many kilonova contaminants. So let's remind the previous classifier. I use both anomaly score and also the maximum probability for each class. So high 1 minus maximum probability means it's more likely being anomaly. So if we use both metrics both metrics, we can significantly reduce the first positive rate. That means there would be less misclassified non-kilonova. So to validate our framework, I use two data sets. One is type 1 supernova is actually observed by our 7-dimensional telescope, and the other one is the kilonova data samples. So for the type 1 supernova, it was successfully classified as a type 1A and also non-anomaly. For the kilonova, except for the earliest one, most of them were classified as an anomaly. That's good, but the earliest one is classified as supernova. This is because they share common spectral features like blue slope and featureless shape. But supernova is rare and it is much more brighter than the kilonova. So it is easy to distinguish them. Also, I put one more interesting task. What if we put the high SNR broadband photometry data on our 70T? Unfortunately, there's no significant improvement, but still LSST is still powerful to detect very faint transients. So this is our take-home messages and welcome comments and any collaboration suggestion. Thank you.
Thank you. Do we have any questions?
Where is it actually sited? Is it in Alsace, or where is the telescope actually sited?
Chile is a nearby Louis LST.
Right, but where?
Is nearby. Sorry, I forgot the name.
Is it the private observatory on the other side, Alsace, or is it?
Yeah.
Okay.
Yeah.
Thank you.
What was the most difficult aspect of developing this multimodal or this project in regards to the diversity with kilonova, the diversity issue when it comes to kilonova?
Oh yeah. Actually, yeah, that's right. So we have no enough kilonova samples, so I have no choice to use the simulated kilonova. So that's why I did not use the kilonova as our just normal classifier. So that's why I'm trying to find the kilonova using the anomaly detector. So yeah. According to the anomaly classifier, I didn't use any kilonova samples. That's the point, actually. Yeah.
That's interesting. Okay. Thank you.
Thank you.
I believe Angelica is next, and she's on Zoom. us 1 moment. Give us 1 moment so we can get the Zoom participant joined on.
Hello, everyone. I hope that the presentation is seen. So thank you so very much to the organizers for giving us the opportunity to share the simple message. LSST already generates data with astrobiological value across all 4 science pillars, and it's time to organize astrobiology as a unifying product of all of these layers. For example, cosmology isn't just about structure, it sets the timeline for life. When we look at the temperature history of the universe, we see that life appeared late after the peak of star formation, just as cosmic acceleration began. So this delay defines habitability window, and importantly, dark energy may have extended it. So LSST with its dark energy mission is actually charting when and where life can arise. So that makes astrobiology already embedded in the pillar 1. But LSST doesn't just map the sky, it builds up 4D map of potential habitability, capturing brightness over time, helping tracking flares, outgassing, and even planetary phase curves. And multi-band imaging hints at biosignatures, even for example, vegetation red edge. Astrometry may capture the binary orbits potential technosignatures. So actually, LSST may be discovering machine for the habitable worlds and priming follow-up with JWST, Roman, and Life mission. Of course, as we moved closer to our planet, LSST makes the outer solar system feel exciting again, but not just about the numbers. It's about chemistry. These bodies, small bodies, preserve the prebiotic inventory of the early solar system. So LSST may filters may overlap with key cometary spectral emission features, allowing us to detect outgassing events and study activity, even for distant KBOs. For example, on the right, each point is KBO in LSST DP03, and a red star marks rate detection of activity in such objects. With LSST, this won't be rare anymore, and we will move from one-off discoveries to systematic census of volatile activity across the solar system, and even maybe mapping how prebiotic ingredients move, mix, and persist across the solar system. LSST decade-long baseline will allow something new, discovering maybe wide orbit planets through stellar wobble. Within 25 parsecs, Rubin may detect milliarc-second level shifts caused by giant planets at 5 to 20 astronomical units from other star. These outer giants shape planetary systems, shepherd comets, protect inner worlds, and may host icy moons with subsurface oceans that may be target for next generation space observatories. The red box shows the region where LSST extends the current frontier of exoplanet discovery. And even maybe astrometric drifts inconsistent with gravity might point to technosignature. Spectroscopy is gold standard for biosignature, but slow and expensive. LSST may open new pathways, scalable photometric screening. LSST filters overlap with the oxygen, methane, and water absorption bands, and maybe even with vegetation red edge. In transiting system, we can use wavelength-dependent transit depths to reconstruct low-resolution spectra. And our simulations show we can extract planetary SEDs using color difference and tensor decomposition. So maybe LSST will serve as a triage engine, prioritizing targets for follow-up of other observatories. M dwarfs are the most common stars and top targets for temperate rocky planets, but flares can strip away atmospheres, like in this pilot case, where cyan points are outliers, may be shifted by excess UV light from the flares of such M dwarfs. This flare-driven displacement will allow statistical filter of unstable stars even without spectroscopy, and focus follow-up efforts of Euclid, Roman Life, and HWO on the most promising quiet systems. Habitability doesn't stop at stars, it's shaped by the galaxies itself. In synergy with Euclid, Roman, and foremost LSST, let us explore galactic habitability across stellar mass, star formation rate, and metallicity, three axes. The Milky Way is typical galaxy for cladding life, as on the left, but LSST may uncover exotic, overlooked galactic cradles of life, just as illustrious simulations suggest that there may be a second locus, a class of low-mass galaxies with unusually high metallicities like Large Magellanic Cloud. So LSST may enable the first statistical census of potential galactic cradles of life. And SETI, we know, faces the cosmic haystack, huge multidimensional research space, but importantly, LSST is maybe a game changer by opening powerful optical window as suggested by many studies like Davenport, Hambleton, and Sheikh last year at Astrobiology and Future of Life meeting. And we already heard about the news about detection of the 9-minute periodic repetition of the signal with 3i Atlas. And LSST already captures astrobiology relevant data in synergy with Gaia, Roman, Euclid, and JWST. It forms multimodal framework enabling AI-driven astrobiology that integrates time, color, motion, and spectra across spatial and temporal scales. And we propose astrobiology at scale, coordinated, contextual, and computational layer within the LSST, formalizing as the LSST Astrobiology Working Group, initiated and led by the UK INCA team. So the mission is to unify astrobiology discovery across domains, from solar to stellar systems to galaxies to dark matter, and make the search for astrobiology relevant and statistically testable science with LSST. And we are gratefully acknowledge support from Europlanet and the University of Kent for this initiative and work. Thank you so much.
Thank you so much, Angelica. Do we have any questions from the audience? Wonderful.
Thank you, Angelica. Very nice and very unusual contribution. So there's been a lot of discussion about technosignatures. And so do you envision this group working both on exobiology and on technosignature, or do you see them as separate topics that require radically different approaches and therefore shouldn't be under the same group?
As for the technosignatures, thank you so much, Federica. The technosignatures are outliers on specific, but the detection of the technosignatures requires actually astrobiologists and interdisciplinary approach. Also, it is important to have protocols for the communication of such detection in order not to undermine the LSST efforts. And all of these protocols are actually important and within the astrobiology. So technosignature is also important part of these interdisciplinary efforts, not only to be separate. And most importantly, within this astrobiology group, we should also have protocols how to communicate findings, to be authoritative in public and to be relevant and to be consistent.
Thank you.
Thank you.
Do we have any other questions from the audience? Double check on Slack. Where do you see the involvement of citizen science with the work you are doing? Where do you see it evolving to?
The citizen science is important part of the astrobiology efforts, and that is already embedded in some other works by colleagues from Spain, involving detection of some specific type of the stars that may be connected to the technosignature. So that citizen science is one of the important parts of interaction between the humans, AI, engines in order to detect the outliers or specific signals that are actually completely different than what a standard AGN science, what standard LSST science collaborations are looking for. So actually, astrobiologists will look at the things that maybe some other science collaborations will think as the noise or some, something that it is not interesting. And there we need help from the citizen science.
Wonderful, thank you.
Thank you.
Vivienne, you are welcome to share your screen and begin presenting.
Okay, I will start to share my screen now. Okay. That's okay. Okay, thank you guys so much for the opportunity to speak for you. My name is Viviane, I'm a postdoc at the CBPF, and today I'm gonna present this working where we made the Hubble constant measurement using the statistical dark science methodology. So to do cosmology with dark science, we basically have the HW event to provide the luminosity measurement. And you also have to combine it with the electromagnetic information from a galaxy catalog so that you can estimate the redshift of the source. So in this methodology, you basically need a complete galaxy catalog in this localization area of this GW event. And also it's going to be good if you have a high quality photos measurement too. So this already applied with the real data. In our previous work, we show that with the 10-mile localized dark science, we can achieve a precision of 20%. In particular, with this work, we decided to use the DESI legacy survey as our galaxy catalog. So DESI is a combination, the legacy survey is a combination of 3 public projects that cover more than 20,000 degrees square, all this orange area that you can see in this figure. We also selected 5 BB8 super event that was detected by the LVK collaboration in the O4A run observation. And together with this plot, we also plot the localization area of each one of these BB8 super events. That is solid line you can see in the figure. And if you compare with the legacy footprint, you're gonna see that the legacy has a broader coverage of this localization area. Unfortunately, we do not have the spec Z for all the galaxies that is inside legacy survey, so we decided to use a deep learning algorithm to estimate the photo Z of this galaxy. So we started to assume that the full photo Z PDF is written as a linear combination of a Gaussian function, and then we ask for the deep learning algorithm to understand how to relate the photometric data with the spec Z, and then estimate the linear coefficient, the mean, and the standard deviation of each one of these Gaussian functions. So this figure shows the quality of our photo Z estimation. You can see that most of the points follow this linear relation between these two quantities. So this really shows that the deep learning algorithm really understand how to relate these two quantities and provide accurate photo Z estimation of this. Okay, to do cosmology, you have to compute the H0 procedure. So basically, you have to compute this equation. You have to define the selection function that carry information about the detection probability. For the prior, we decide to use a flat over this range, the GW likelihood to written as a Gaussian function, and the electromagnetic likelihood is just a product of this full photos PDF. So this figure summarizes our final result. You can see that the green solid line is the result of a combination of 15 dark stars. This provides H0 uncertainty of 12.6 that could be compared with the result of the bright star one, 12.3. And then we also combine these 15 dark stars with the bright stars, and then we get this black solid line that has a precision of 6%. So the amount of information that the dark stars add on this bright star one causes a reduction of 13% in this H0 uncertainty. Next, we perform a systematic analysis of this dark starring methodology. For this, we simulated 100 dark starings detection by the LVK, left side for the O4, right side for the O5. In all of them, we just assuming that all these galaxy redshift are perfectly measured. So our results show that it's possible to recover an unbiased H0 measurement with this methodology. And also when you assume the stellar mass as a trace of these GW holes, our forecast indicated that it's possible to achieve a precision of 3% for the O4 and 1% for the O5. Start to see a very high bias when you start to have a very complete galaxy catalog, and you can see that that you have a shift on the at a low H0 value. We show that you can correct that, just add threshold on this absolute magnitude, and then you stop to see a shift on this H0 procedure peak. Finally, we start to study the photos uncertainty inside this dark science methodology. We decide to look for two different scenarios here. A conservative one, that is the blue solid line that you can see in this figure, and an optimistic one, that is the orange line, okay? So you can compare with the result that you already have with the full photos PDF, that is the black solid line. So you can see that the blue is very far away from the result that we already have, and the optimistic one is more closer with these results. So as already expected, when you put the photo zero on these dark stars analysis, the H0 procedure become less informative. And also we noted that this photo Z uncertainty effect start to dominate the effect of this host galaxy weighting. This is just a preliminary result. What we may be found with this in the LCCT era. In this case, we assume 15 golden dark stars event. When we also assume the stellar mass as a tracer here, and our forecast indicates that when you have a conservative scenario, it's possible to achieve a presence of 29%. That could be reduced to 6 if you have an optimistic one. And if you assume a really, really optimistic scenario, it's possible to reduce to even 4%. Okay, I will leave my conclusion to you guys and I'll stop here. And thank you so much for your attention and thank you for the opportunity.
Do you have any questions from the audience? Which aspect of this work has proven most difficult?
Most difficult is to control the photos uncertainty, of course. Yeah. And also the quality of these H0 constraints gonna depend of the completeness of this galaxy catalog, and also if you can control these photos uncertainty. So it's gonna depend of these two main effects here.
Could you continue speaking about that?
About the incompleteness of the galaxy catalog?
Yes.
Yeah,
what
because
okay. Go ahead.
Basically, the methodology also depend if you have a galaxy in the localization area of this GW event. So if you don't have, it's kind of problem because you start to see a very your results gonna depend of this, okay? And also if you have a very broader photo Z uncertainty, okay, the H0 constraint is gonna be worse also, because you have to see the structure inside the line of sign of these events.
Thank you. Jeff Newman has a question on Zoom.
Yeah.
Yeah, I wanted to ask if you've looked at using existing samples that have stellar mass estimates as well as photo Z. So Rongpu Zhou's photo Zs for the legacy survey, for instance, we have stellar masses for everything down to Z of 21. By exploiting the WISE imaging in particular helps a lot with that. So have you looked at using stellar mass already?
No, for this real, for the result that I show here, I'm not using a stellar mass as a tracer yet, but I will do in the next work that we are doing. But I'm just testing stellar mass as a tracer in the simulations data.
I see. Thanks.
Okay.
Wonderful. Thank you, Vivian.
Thank you.
Simran, you are welcome to share your screen and begin presenting.
Hi, let me just share my screen. Can you see my screen okay? Can you hear me okay?
You're able to.
Hello, everyone. My name is Simran. I am a PhD student at University of Michigan. I'm working with Marcellus Soares Santos at University of Zurich. And this project is on the simulations that I've been doing to predict the Hubble constraining power of LSST, particularly with the bright siren simulations. So with LSST, we are going to be in a very unique and optimistic position where we would be able to follow up the gravitational wave events. And with that in mind, particularly for bright siren discoveries, which are basically the binary neutron star events that we could detect, we want to predict how much of an improvement we can get by using LSST as a probe for following up the gravitational wave events. Also, during the survey of LSST, we have the expected overlaps with future observatories, the future LVK upgrades, and Einstein Telescope Cosmic Explorer. And the overall goal is to obtain a recommendation for desk cosmology results in order to maximize the scientific return. Also, to note that with the first discovery of the GW17O and 17, even though we had optimistic predictions for BNS detections, this is like an ever-changing scenario. So this is very sensitive to the detector upgrades and how things go in the real time. So with the simulations, I am trying to simulate the binary neutron star events here. And these involve the gravitational wave simulations, which is the first point of contact with these binary neutron star events for us. For this, I'm simulating the realistic binary neutron star population with the Fisher analysis to obtain the parameter forecasts. Once we have that sorted out, we look into the electromagnetic counterparts, particularly kilonovas in this case, where I obtain the ejecta parameters and then use the Bullard radiative transfer models. Combining these two informations, the idea is to get joint Hubble analysis for detectable events, also incorporating the selection effects, which the multiple selection effects that can come up and give us some realistic constraints on the Hubble measurement. Starting with the gravitational wave simulations, I first simulate the redshift distribution using the Maddow-Dickinson profile and time delay distribution with this minimum time delay of 50 mega years, and the distribution peaks at lower redshifts with this configuration. Then for BNS, we have 13 parameters that can be detected with the gravitational detector. Involving the masses of the two neutron star, luminosity distance, spins, the tidal deformabilities, among the other inclination angle also, which is very important here, Theoretically, we should be able to detect all of these, but depending on the sensitivity of the gravitational wave detector, we can have less constraints on certain parameters, for instance, the tidal deformability. But the parameters which are of most interest here to me are the luminosity distance and the inclination angle, which can also affect the, which kind of encodes information about the how the binary is inclined with respect to the detector and how it can affect the degeneracy between these two parameters. Now, with the gravitational wave detectors that would be of interest to us during LSST, it includes the future LIGO upgrades, which would cover most of the LSST survey itself. And towards the end, in 2030s and probably beyond 2035, we can have future gravitational wave observatories, which predict a large improvement in the BNS detection rates, which would help us create a big data set of BNSs to look at. With Einstein telescope in mind, for now, I'm simulating 10⁵ events, for which I have a couple results here. So in order to do this analysis, I'm using a Fisher analysis code called GWFAST. This helps me calculate the Fisher matrices, the signal to noise ratios, and also the sky localization areas, starting with the 10⁵ 100,000 BNS simulations with just ET as a detector for 1 year of ET observations, Einstein telescope observations. I get the SNRs and apply a cutoff SNR 12. This cut is chosen because the Fisher analysis itself is only reliable for high SNR events, and we do lose a bunch of events here given the large redshift that was used to simulate these. Then there are multiple cuts that are happening here that also involve some technical issues that come up with the Fisher calculation itself. For example, while obtaining the covariance matrices, certain Fisher matrices are very ill-conditioned for inversion. So we remove certain events which have the inversion error greater than 0.05 here. Then looking at the parameters, luminosity distance and inclination angle, here the errors get into the unphysical ranges. So we try to avoid those events which have unrealistic 1σ errors. For example, negative luminosity distances getting into the 1σ range, or the 0 to pi inclination angle values beyond that range. So we remove all these events, we are left with comparatively less number of events than we first simulated. And this is the initial Hubble diagram with the luminosity distance and on the y-axis and the redshift on the x-axis. Of course, the errors are error bars are very big here. And another thing to note here is that the sample is getting biased at this point, and which is currently under investigation to see what could be affecting it. Either it could be the Fisher matrix formulation itself or some other selection effect coming into play here, which is an interesting observation here and also under further investigation. Then considering that we have taken care of the gravitational wave simulations part, next step is to obtain the electromagnetic counterpart modeling and simulations. For that, we first obtain the parameter mappings using the empirical estimates in the literature, particularly with this Setzer 2022 paper. And this plot shows the distribution of the total ejecta mass compared with the ejecta velocity for a kilonova. And of course, this shape is a bit complicated to explain, but it has a lot of information which needs to be further decoded. Then we also use the Bulla-ICD models to get the approximated light curves for these BNS events. The most important thing to address in this section is the detection criteria for classifying an event as being detected by LSST or not. where we want to be as realistic as possible. So the first thing to do here is to that we are applying is the Rubin target of opportunity strategy, which was formulated last year at Rubin community Rubin TO workshop. And particularly, we are planning to follow up the gold events, which have sky area less than 100 square degrees, and the silver events, which have sky areas less than 200 square degrees. And another ideas that we have in mind for a realistic detection criteria is maybe try the source injection with DP1 images.
You have
or
30 seconds.
Oh, okay. So source injection with the DP1 images or some simulations of the background effects of supernovae, etc. Yeah, so this is work in progress. Other than the EM modeling, the detection criterion, we have these selection effects that need to be taken care of to have realistic constraints on Hubble parameter. And these extensions are underway, and the goal is to support the test cosmology goals during LVK 05 run and also beyond. And that's my time, I guess. Thank you so much. And also feel free to check this Rubin Research Bytes poster on the same topic that I have linked here. Thank you. And let me know if you have any questions.
Do you have any questions in the audience on Simran's project? Let me check Zoom. Could you go a few slides back for me on the one more, that one. One more forward.
Oh, sorry.
Yes.
Yeah.
The Hubble diagram, the two versus observed cosmology. Could you expand more on the bias that you aforementioned?
So the black points here are basically the true cosmology using which I have simulated the data set. And the blue points here are the sampled observations. So centered around the true value, I have drawn events with the uncertainty that I get from the Fisher matrices. So these are single draws from that multivariate Gaussian distribution of luminosity distance and inclination angle with other parameters marginalized over. So we can see here, instead of being centered around the true cosmology, there is a bias due to which I have not added those results here, but I'm getting Hubble constraints which are not very realistic and very biased. And yeah, this is something that I realized recently. So this is under investigation, and also try to understand what would be causing this. One idea that I actually received in the desk meeting last week was to increase the sensitivity of my detector just artificially and see what happens in that case. So yeah, compared to the true cosmology, the samples are biasing towards a different Hubble value here. If that answers your question.
That's fascinating. Thank you. Do you have any other questions from the audience? Well, with that, thank you so much, Simran, for presenting with us. Toma Ahumada. Wonderful. Thank you, Simran. Technical difficulties, give us one moment. the restroom or to get a glass of water, feel free. We are going to upload Tomas' presentation.
Great. Sorry about that, guys. Well, hello, everyone. I'm Tomas Auma. I'm a postdoc at Caltech. I'm working, and I'm thrilled to be here presenting our searches for gravitational waves, for optical counterparts of gravitational waves with the Zwicky Transit Facility. So if you're here, you probably are familiarized with 17017. So I just wanted to mention that it happened during 02. It happened at 40 megaparsecs, and it was localized to around 30 square degrees. That changed dramatically in 03 and 04, as you see here. The gravitational wave 190425 was detected at 150 megaparsecs and was localized to 7,400 square degrees, which is quite localization. In 04, there's this one detector event, 230529. It was detected at 200 megaparsecs and basically covered half of the sky, 24,000 square degrees. Based on that, on the large localizations that we are getting, we're using the Zwicky Transit Facility, CTF. So I'm just here showing CTF in comparison to other state-of-the-art wide field imagers. So you have Rubin there. The Rubin footprint covers 9.6 square degrees, whereas CTF covers 47 square degrees. So you can see why is this so efficient in terms of searches. CTF covers the entire sky every 2 nights. So here I'm showing a random just simulated sky map of a gravitational wave, and I am plotting the nominal just random coverage of CTF on one random night. So one of the strategies that we've approached is, instead of relying on the serendipitous coverage that it's between the random night and survey that we're covering, it just maybe why don't we take all these fields and just reweight them and use them to cover a much more optimal sky region of the gravitational wave, but without interrupting the survey. So just like rearranging the fields that will be observed anyways, just tackle them at a different time. So this strategy allows us to use the CTF survey. Nominally, it's a 30-second exposure, and it generally goes down to 20.5 magnitudes in R band. You have here also the gravitational wave 17817 light curve scaled to 200 and 400 megaparsecs. On top of that, we can also just trigger 300 seconds observations through our target of opportunity. And you have here 230627C. It had a very elongated sort of localization. We were able to cover that with around 10 pointings with CTF, and we covered 75% of the localization. With those 300-second exposures, we can get down to around 20-second magnitude. So everything is sort of like orchestrated through Sky Portal. If you are a fan of astronomical software, I highly recommend you to read Michael Coughlin's paper, Coughlin et al. 2024, which is where we describe Sky Portal, our instance of this astronomical tool. It's called Fritz. That's why the name is over there. But it allows us to interact not with just the CTF data and other surveys. You can request for photometry. You can see what's on TNS and things like that. You can also receive sky maps from GCN, and allows you to sort of like play around with the observing plans and submit them to the telescopes. And it's not just for CTF. We have been using that for our DECAM follow-up as well. So once you submit that to the telescope, you now have to deal with the stream of alerts, similar to the alerts that you'll get with Rubin. There's a bunch of metadata that you can use to sort of filter out stuff that you don't think it will be related to it. In this example, we covered 2,900 square degrees. We found more than 170,000 alerts, which is a huge number. And after this like very simple and automated filtering, we're left with 300 sources, which is much manageable. However, we haven't really been able to find a kilonova candidate, a compelling kilonova candidate during O3 and O4. However, we do have limits with CTF and other surveys as well. So here I'm showing the light curve space for G in green, R in red, and I in yellow. You have the different light curves generated by the BULA models, where basically I'm using the CTF limits to rule out these light curves as non-related. These light curves come from a parameter space that we basically tells you what sort of ejecta masses you can basically rule out with your observations. And in this case, for 230529, which was an NSVH at 200 megaparsecs, where if it happened within the volume that we actually surveyed with CTF, we can confidently say that this geometry, the viewing angle of less than 26 degrees was not the case. So currently, we're also trying to use the same approach to combine limits from different surveys. That could also be the case for Rubin in the future. In this case, in a recently submitted paper, we analyzed 250206 DM. It happened at 370 megaparsecs. Both CTF and DECAM observed. CTF observed a little closer to the merger. So you have here shallower observations with CTF, and then a few days after DECAM comes. And the combination of those two surveys allows us to rule out around 55% of those kilonova models that live in this sort of region of more massive models. And with that, I just wanted to mention these few papers that have much more in-depth analysis, and just look forward to what Rubin can help us, both in trying to find the kilonova, but also maybe try to constrain the kilonova parameter space. Thank you.
Do we have any questions from the audience? Everyone must be, oh, perfect. Everyone must be really tired from lunch.
Thank you for a great talk. Very love question, but which kilonova models did you use? And the other question is, do you consider the AND gate or OR gate to when you constrain each pointing? So yeah.
Can you read me the first part of the question?
Yeah. Which models do you use?
We're using the BULA models. So they were presented in the first grid, I think on Shreya's paper in 2020, the analysis of those two NSVHs. But yeah, we're generally using those. And what was the second part of the question? Sorry.
Okay, can you go back to that slide?
This one?
Next one. Yes. When you constrain each models, do you consider each point?
Yeah, this is a fun. I understand. So this is a this is more like an approach of what we could do when those surveys actually look in the same space.
Yes.
These are disconnected regions, so it's just like a prospect of what we do in terms of combining data sets.
Yeah.
If you see here, DECAM observed this lobe.
Yeah.
Whereas CTF observed a different lobe, so they're disconnected. So this analysis could be happening in terms of.
Oh, I see.
Yeah. In the future, we can use 7D data that whatever other survey and try to use that to constrain.
Yeah. Because when I do this similar analysis, the OR gate has much worse.
So we do
constraints.
We do have another analysis which is in the paper. I didn't have time to talk about it, but we call that it's the SIM survey analysis basically, and that's why when you inject kilonova models and then compared to what your observing logs do, and that's when you actually it's an AND instead of so basically it takes everything into consideration and see what models survive and what are your efficiency at recovering things from your observations.
Are there any more questions? Alrighty, thank you, Toma.
Cool, thank you guys, and sorry for.
And then we have me giving the last talk. I put myself last in case we went over. All right, well, hello everybody. Last talk of the session. And so I'll be discussing the Vera-C-Rubin Observatory and its ability to detect kilonova, as well as the evolution of these metrics. And so like the model I was referring to, I use Mbula's models to begin to create light curves. And then we vary and create a diversity, create a diverse array of these kilonova by varying the dynamic and wind ejecta, as well as their phi and theta angles. As well, when I was creating this population across the universe, and so we have to create a uniform sky, I applied a BNS merger rate for a volume of about 1 million events, 10 to 1200 megaparsec distance, and with using the O3 BNS merger rates. And this was from my 2024-2025 paper. And so obviously we have, been involved in O4, and so we were waiting to see what those numbers would be. We have not detected anything, but this is just an estimation of the capabilities that Rubin has for detecting these very faint and fast transients. And so detecting fast transients with Rubin began with kilonova. So Igor Andreoni released a paper in 2019 with a set of metrics, multi-detect color, red and blue, which were generic transient metrics, so 2 detections of a fast evolving event, and then with red and blue filter specifications. And so we could begin to see what was Rubin picking up with the most generic of detection criteria. And then we had some more specific detection criteria called ZTFRS simple, which applied a limit to its rise and fade rate. So we were looking for something that was rising faster than 1 magnitude per day and fading faster than 0.3. And then that also had a subset of ZTFRS simple red and blue. So we're looking at those same criteria, but in red and blue filters only. And so over the course of about 18 months, I tested the efficiency of these metrics to various cadences that the SCOC was releasing. And then the paper was published in February era. And so we were able to test the last of it, V3.6. And so when Rubin added this very real skew to it, or slew to it, so its ability to move and target something, we saw this nosedive. But that has changed. And so with the BNS merger rates from the operating run 3 of LEGO, Virgo, and Kagra, we had a optimistic multi-detect, so that's that generic metric, about 128 detections. Optimistically, we had 14 for ZTFRS simple. And so these numbers obviously get worse when we decrease the rate of the density of these events or these light curves in space. However, about a year ago in October, so there was some overlap with these 2 projects. When the fast transient subgroup was restarted, thank you, Sharfed, I was tasked with building metrics that were more attuned to individual science cases. And I had many years of experience, much support from Michael Coughlin and Igor to begin writing my own set of metrics based on the aforementioned ones. And so I took a look at what we were doing with the old runs, the old simulations, and I decided to create a scaffold. And so we emulated we simulated light curves of kilonova using the Mbula models. We used catalogs from GRB Afterglows and others. And then we model populations on an injected uniforms map of the sky. We apply Rubin's footprint, its cadences, and then we filter the population through detection criteria. And then once we have those set of detected events, those are then pushed through with characterization criteria. And this varies depending on the science case, and I'll discuss what we have chosen for kilonova in the next slide. And then once we then run the metrics on these cadences. This is ongoing. And then we retrieve detection efficiency between cadences of interest. So currently we're doing 3 versus 4 rolling cycles versus no roll. So now we have the original 14.6.1 for the kilonova specific detection criteria that was in the older version of this paper. And that was pretty slim pickings. But when we moved these ETFRS simple criteria to the detection instead of a secondary mode, we actually were able to retrieve more. And these numbers are with the median estimate, so about 105 10 to negative 9 megaparsecs per year. And so we have now we're looking for 2 detections with an SNR of 5, with a rise of 1 and a fade of 0.3. And then for characterization criteria, we really looked at what the behavior is of these fast transients and took a few different color evolution tasks, and we applied it to this characterization criteria. So we have these ETFRS simple criteria now as detection. So we have the population, we filter it through, and this is populated all over the sky. So not just within Rubin's footprint, so all over the universe. And so we filter through that population with the ZTFRS simple detection criteria. And then the characterization criteria requires greater than 2 distinct color measurements, so filter pairs. And then we have it separated by greater or more than 3 days, and that same filter pair or 1 overlapping filter with a redder second one. And then all detections have to be greater than 5. And we're actually retrieving a good number of them. And so these are preliminary results. We've just begun to finalize the theory that we're using for characterization criteria. But it is hopeful that with these new cadences from the SCOC, that from baseline V3.6, that we're improving our numbers. So we had a nosedive. We haven't been really seeing any during 03 and 04, but we're hoping that this is an indication that Rubin's capabilities will surpass that of what we've seen. Thank you.
Thanks for the talk. It was very interesting. I just wanted to, I was wondering if you have explored, because when you create your universe, you're relying on the Rubin cadence, right? Have you tried to just sort of like force a target of opportunity, for example, so that you can get like the first detection or the first observation and see how that changes your metrics?
Hello, it's working. Could you restate the question? Because if you're asking if we have done or modeled, just a target of opportunity survey to see if something could be caught, then no, we have not done that. This is just using the most recent baseline V 4.3 and 4 roll 4.3 to see if we can detect anything.
Do you think it would be hard to do it? Or like, is it technically?
It depends on what is on. So the cadences are not manufactured by us. We adapt the metrics and the script to run the metric analysis framework. But that's an interesting question to see what would the aptitude be for target opportunity or like the micro surveys.
Yeah, thank you.
Thank you. Great question. Lynn Jones on Zoom asks, are these metrics still running within MAF? I don't know. There were some issues as the Rubin Sim version has evolved. There were some issues running the older metrics, and so we've had to make some adaptations as we've evolved. But that is a project that Fed, Shar, and I are taking care of later this summer.
I have a question and then an announcement. The question is, can you, if I asked how many kilonova we'll find in 05 with Rubin, what's the answer? No, you can put any error bar you want. I want to, okay, that's what I wanted to know. Do you agree?
I like
I
the
said
question.
05.
We can choose to be optimistic. We can choose not to be. But I have no answer for you. But Fed, go ahead. Let's get somebody deliver Fed a microphone.
I don't think the estimates that we had when Igor wrote the first paper on this are dramatically changed. So from depending on the rates, it will be from a few to a few tens. You said whatever.
Okay, so a factor of 10. Okay, good. And the announcement is we're going to observe this binary black hole tonight at Rubin. So stay tuned.
Great ending to our session.
Come on.
Bob, is it going to be live streamed?
Like
Like a black screen, just live streamed?
No, it's not going to be live stream, but we'll try. We're all here this week. We'll be watching. We'll tell you what we find out.
All right, it is 2:52. We are on time. Thank you, everybody, for joining this session. And a round of applause for our speakers. If you have any questions, please feel free to keep using the session channel for questions and interactions with our speakers. Thank you.